Z-scores, what they tell us about probability. So, what exactly is a Z-score? Well, in general, the basic idea of a Z-score is that we would want to know how many standard deviations away any given data point is from the mean of the data set. But the next logical question to ask is, why the heck is knowing how many standard deviations you are away from the mean, how that gives you any information at all? And so to look at this, we need to know about how to analyze the standard curve. In general, the standard curve is just a graphic way of representing the spread of a data set, and if you take the area underneath that curve, it gives you the probability that a certain event will happen. So here we have two different standard curves, one with a small standard deviation and one with a larger standard deviation, and the idea of having these different curves is you can obviously see that the smaller standard deviation, the data is more compact, and with the larger standard deviation, the data is more spread out. Yeah. So, of course, as we said before, the standard curve gives us a graphic way of representing things, and on a traditional z-score chart, you have a bunch of numbers that pretty much look weird when you first look at them, but they're quite interesting. A key fact about a z-score itself is that no matter the value of the standard deviation, the number of standard deviations still gives you the same probability. So going back to our previous curve, if we have a situation where if we're looking at the right side of the red curve and the right side of the red curve for both the small and large standard deviation, the area, which can be interpreted as the probability of the event occurring at one standard deviation, is the same. And of course, this is based on scenario. There are many different scenarios in which this will help you, and in many different data sets. For example, the SAT itself has it uses z-scores and the idea of the standard curve to distribute the weight of the exams, while being within a certain number of standard deviations. When you take the probability, that gives you the percentile that you're in, and whereas if you have just a regular old event regarding the weights of tomatoes, for example, then finding the area underneath the curve gives you the probability that a tomato would have a certain weight. So now it's time to look into the equations for the standard deviation, and I don't want to bore you with all of the weird looking equations here, but basically looking at this little diagram I drew off to the right, you have that the data point, the distance from the data point to the mean can be represented as that data point and subtracting that data point from the mean, which would give you the distance. But we can also interpret it as, if we were using the idea of z-scores, that the z value is the number of standard deviations you are away from the mean, and if you multiply that by the standard deviation, you're going to get the same, you're going to end up in the same place, which then you can divide both sides of the equation by the standard deviation, and you get the beautiful formula you have off to the left, which is that z is equal to the data point minus the mean divided by the standard deviation. Now, why look at this equation? The most interesting fact that I thought of when looking at this set of equations is that nothing in these equations is specific to one standard curve. So the calculation for a z-score doesn't really matter what the standard deviation is. You'll still have the same area underneath the curve up to a certain standard deviation. Now, the data points might be more spread out, but at one standard deviation for both of these curves that we have here, you will have the same probability, and it doesn't rely on anything specific about the standard curve. We just need to know a data point where the mean is and where the standard deviation is, and we can find the probability that a certain event will happen, which is pretty cool.